And now, after successfully addressing all the key points or highlighting all the key points regarding comparing two population means, then we are now ready to apply our skill or bring our understanding into doing an actual example. So allow me to actually use the exact example, the information that I brought up throughout the general discussion earlier as a formal example. And so now we're going to be ready to set forward with this current example over here. So by far we have learned that, so in our sample, in this study right here, we're studying about the population mean age for reaching high blood pressure, HBP. And so we isolated our beginning population into two separate populations. So there's the male patients population, or the man population, and there's the woman population that we call these the female patients. So these are samples that are selected from the two separate populations correspondingly, as indicated here. And then, so for the male sample, we collected 400 as the sample size, and we measured and we found the sample mean here in this sample from population 1 is 42.5, and the standard deviation from of this sample from population 1 is a 3. And so in connection with what I've discussed earlier, then we currently use that convention that the male population or the man population was decided being to be the population number 1. And so on the other hand, that means on the female sample over here, which is selected from the woman population, then our sample size here is 400, and we call that this is N2, and this is the mean of the sample that's collected from population 2, and so, or in other words, this is X bar 2, and then this is the standard deviation of the sample that was collected from population 2. All right, so here we are back to our quick summary of the information that I have addressed, and I used this information throughout our general discussion of comparing two population means right here. And so again, just like how I explained earlier, mu here generally is just the mean age to have high blood pressure or HBP for anyone. And then we particularly separate our study. We particularly would like to study this mean value on two separate populations. So naming population 1 and population 2. So these numerical labels are what I initially decided to give for the two separate populations here. And so all that information is here. And so we can anyone can roll back to the earlier part of the video to understand how I gave all of these subscripts right here. But so now, according to the definition of D and D bar that I have given earlier, and I still retain the highlighted definition of those here, plus the understanding that samples that we decided from population 1 does not need to equal sample size on samples that we selected from population 2. So N1 does not need to equal sample size N2. That's what this other than symbol is for. Not equal to symbol is for. And so in that way, we're understanding then straight out from this definition, and particularly D bar is defined to be any sample mean from population 1 subtract a sample mean from population 2. So that means right here now, particularly in our actual example that we're about to get started, then we can sketch out further information. So according to this understanding, then we are looking at, we have already a value, and my wording I'm saying is what I have here is a value for our D bar. And so in this way, how D bar is defined, then I'm going to take my sample mean value that I currently have from population 1, which is 42.5. I am going to take the difference with the sample mean I'm currently having from population 2. So that's 51.2. And so this is just whatever this difference turns out to be. It's going to be just one among infinitely many other differences in sample means out there. So any of the difference, any of the d bar values is going to be the difference between x bar 1 and x bar 2. And so calculation gave me negative 8.7. It's a difference, so it makes perfect sense to have a negative difference in the two values. So what it says, at least what it says right now, before we go on too far, at least what it says right now is that based on the two separate samples from the two separate populations that we are currently having in hand, that I am currently having in hand, then the samples are at least showing that man comes to high blood pressure on average earlier than woman, because that difference here is a negative difference, or indicating that in our sample the mean age for a man to have high blood pressure to develop HBP is less than the mean age for women to develop high blood pressure or HBP, and that's what resulted in this negative 8.7 difference in the samples. But as I said, this is only maybe our sample. Maybe this is our only sample that we've had. Maybe other samples, who knows, it changed to different values. Now back on this screen right here, then now we are ready for getting into the actual question regarding the given information here. So right here it's only given information regarding our two samples, and the two samples are everything we have. And so question A now, at significance level 0.001. So this now rings a bell that the problem we're doing here is a testing hypothesis problem right here, because we have a given significance level. And so again, I have to emphasize that this lesson can only be successfully learned for those viewers who have already viewed my other lessons, or have already had background in what it means by testing a hypothesis problem. So at significance level, so alpha here represents significance level. At given significance level 0.001 are the samples, the two samples that we're having here, are the samples showing strong evidence. So once again, we want to have as a yes or no question, are the samples showing strong evidence that mean age to have HBP, mean age to have high blood pressure in female is greater than that in male. So mean age, let me really extract the word right here. Mean age to have HBP in female. Quickly on my scratch work on the writing board here as a scratch work. So mean age to have HBP in female, but that means the question is saying that mu2, we're trying to prove that mu2, mean age to have HBP in female, that's mu2, is greater than that in male. That in male means mu1. And so saying that mean age to have HBP in female is greater than that. So directly right out from the wording of the question right here, we're looking at a statement trying to prove that mu2 is greater than mu1. But so in this way, mu2 is greater than mu1 is the same as saying that this is the same logically as saying that mu1 minus mu2 as a difference. Because recall from the general discussion I pointed out earlier that we always want to set our comparison. So this is a comparison right here. We want to compare and we want to see, we want to prove whether or not this comparison is true, is any strong evidence to show that this is a true comparison. But we now see this comparison as comparing a difference between always mu1 minus mu2 to be in this way algebraically less than 0. But mu1 minus mu2 is what we have already defined to be the difference in the two population means. So mu1 minus mu2 equals d. So now with all that understanding, now we have formulated for ourselves and combined together with our past experience in testing a hypothesis, then the statements we're trying to prove here has an inequality. So it's now going to take its place in being the alternative hypothesis, H1. So now H1, we have a statement saying D, we're trying to prove that the difference right out from the wording here, then we're trying to prove that the difference in the two population means is a negative difference. And so now again, utilizing our past experience with proving a hypothesis, then anytime we have already recognized our alternative hypothesis, then we can easily come up with our null hypothesis here by simply restating or rewriting the alternative hypothesis statements, but with the inequality replaced by the equal sign. So now we have successfully identified our two hypotheses here. And so you have to understand, anyone viewing this video must understand that being left tail or being right tail is no longer one of the main concerns to be addressed in a problem here. We just have to be ready for any case, whether we're working with a left tail or a right tail, because right now obviously it's a left tail. The problem here that we will be using in old term, this is called a left tail test. But my point now is that we have come to use a left tail test simply because ultimately I have decided that the population 1 is to be the man population and population 2 is the woman population. And so consequently mu1 minus mu2 in our case right here is the difference, and we're trying to prove that the difference is below 0, as according to the statement saying, again, mu2 is greater than mu1, right from the wording of the problem. And now I am going to move on further, and again, it is extremely important that anyone following along with this video here must bring back your past experience with testing a hypothesis, because this problem in the end turns out to be entirely a problem where we test a hypothesis. So the hypothesis here, alternative hypothesis here, says the difference mu1 minus mu2 is less than 0, where the null hypothesis is saying that the difference mu1 minus mu2 is equal to 0. Now think about the logic a little bit here before I move on further, that it makes perfect sense to have a null hypothesis stating that d equals 0, because here in this particular study we are studying about a comparison between man and woman populations, but in the end, being a male or being a female, we're all human beings. So it makes perfect sense to assume that all males and females, being the same as human beings, reach to the same age on average to develop high blood pressure. But now, since we have advanced technology that can help us do some further calculation, let's find out if what we have assumed here can be any longer truthful, or it must be argued otherwise. And that's the whole idea of a hypothesis. Again, testing a hypothesis. So now I am going to start out by saying, and with the same technique we've always been using for testing a hypothesis, I'm starting out by saying that if we're letting h sub 0 to be true, so what if h sub 0 was true? H sub 0 is that statement right here stating that the difference in mu1 minus the difference mu1 mu2 is equal to 0. If that statement was true, and further that d bar here is a difference in an x bar 1 and an x bar 2, any x bar 1, any x bar from population 1, and any x bar from population 2. So d bar generally is different, but it's a random variable that represents that. And so we now know that consequently, if d equal to 0, then the extended central limits theorem that I have mentioned briefly throughout the general discussion will imply immediately that consequently the average, or the center of all sampling differences here, the center of all d bar values, must equal consequently D, or in this case, equal 0. So that's one thing we know for sure as a consequence. Once we are letting h sub 0 to be the truth, once we accepted that in the beginning, that if D equals 0, then consequently mu d bar will equal 0, or would equal 0. And as I have emphasized earlier, unfortunately, we're working completely without knowing any sigma 1 or sigma 2. And so here we won't be able to find, and again, I'm clearly saying that we won't be able to find this value. So we won't be able to find that. But instead, we can substitute this by a close enough approximate of that I call the SEC. Now, that stands for standard error. I use a subscript C right here to indicate, to bring up the sense that it's a combined standard error, because so again, as I have explained earlier in the general discussion, most of the majority of professors and stat instructors out there only refer to this simply as the standard error. But for my students, I prefer to call this it's a combined standard error, because it in a sense that in the formula itself, it kind of combines the two sample standard deviations together. And so doing that will keep it easy and simple for my students to understand. It's easy to remember. And so this can be used as a close enough substitute for sigma d bar in place of the average spread. And so now with this setup right here, we can actually calculate the actual value. And so we have already found that S1 is 3. So we go 3 squared over 400 for a sample size N1, plus 4.5 being S2, our sample standard deviation from population 2. And we are squaring that and divide it by 400, which happen to be equal, but this is the sample size that we decided to select for samples from population 2. And then that addition there is going to be inside a square root. Final calculation of mine came out being 0.27041.6, and a lot longer. And unless being specified otherwise, usually throughout all of my lecture videos, I am going to round these SEC to 4 decimal places. So 0.2704. And so again, this value that we have just now calculated is acting in place of the average spread, even though it's not exactly the value there, but it's a close enough approximation of our sigma d bar, which we were unable to find due to the fact that we never knew our sigma 1 and sigma 2. And so now that we have had center, and at least we have had an approximate of our average spread on this sampling distribution of all sampling differences in any x bar 1 and an x bar 2, then again, imagine that if we are on a bell curve representing all sampling differences, so this bell curve here on the horizontal line right here, it's any value of a d bar that we can place there. The center for this bell curve will be for sure at 0, according to the extended central limit theorem. And we don't know the actual sigma d bar. But now this can be used as a close enough approximate, and I will show how to find that, how useful that close enough approximate of the sigma d bar is. But so in that way, now we can see clearly that our actual d bar being negative 8.7, which came out from previous calculation that I have shown, must stay somewhere on the left-hand side of the center of this bell curve right here. And so in that way, we can go ahead and now calculate. So from where our d bar currently stands, I am going to subtract the center on our bell curve and divide that by, instead of the actual precise sigma d bar here, I'm going to divide that by the SEC we have already had. So divide by SEC right here. Okay, and so or as an actual calculation setup, it's going to be negative 8.7 divided by 0.2704. So that's, again, this is our sampling difference in two samples minus the center of the sampling distribution of all sampling differences. And then we divide that by the SEC right here. So this value, whichever the final value would come out to be, is referred to as the T star. And so the reason I keep emphasizing that we need to reveal all of our skills of testing a hypothesis, because all the steps here will be familiar to any one of us. Viewing the video here, once you have already seen how I test a hypothesis without a sigma value. And normally over the web or throughout many web resources, people refer to this testing technique here as a t-testing procedure, or for short, a t-test. So in the end, this calculation setup is called a T star. So final calculation of mine shows minus 32.175. So the truth is, a calculation like this gave me a much longer decimal expansion, but unless being specified otherwise, throughout all of my video lectures right here, I am going to round T star to 3 decimal places, as in this case right here. And so our T star I use here is negative 32.175. But for any viewers, make sure when you are doing a problem like this, make sure you're watching out for your own rounding requirements. And so now the next step is to find the degrees of freedom for our two samples. But the difficulty now is that our degrees of freedom can no longer be n minus 1. We can no longer stick with this way of finding degrees of freedom simply because we have two different sample sizes from two separate populations. We have n1 and n2. So if it's just simply n minus 1, then which one of n1 and n2 will be chosen for n minus 1? There are a few different options how to find the degrees of freedoms in case we have two independent samples like this. I chose to teach students of mine as well as viewers to this video lesson the option that comes with a somewhat messy formula. And the reason I chose this is because I believe any one of us viewing this lesson must be given an advanced software or technology of some kind to handle this calculation. So a messy formula won't be any longer a challenge, but on the other hand, we'll get the most accurate result for degrees of freedom. And so for degrees of freedom, we are going to use the following formula. S1 squared over N1 plus S2 squared over N2 all squared. And that's not all there is for the degrees of freedom formula. We are going to divide by 1 over N1 minus 1 multiplied with S1 squared over N1 and square again plus 1 over N2 minus 1 multiply with S2 squared over N2 and square again. So we are at a very beginning course in statistics, so allow me not to explain how statisticians out there long before I start teaching stats decided to use this formula and proven that this is the one that gives the best precision in case that we're having two independent samples. But so Of course, for public viewers out there, you can use any technology to quickly calculate this. And I will not ask my student to go through a formula like this either. So normally, when it comes to degrees of freedom for two independent samples like this, I have developed a program that runs with Microsoft Excel, and that's called the DF program. So for students of mine who can have free access to this program, once you open the file, you can click on the DF tab at the bottom, at the bottom of your file on the screen here, and you can see that I have the DF tab right here. And so I have prepared 4 boxes because these are, think about the formula itself, even though very ugly looking, even though very complicated looking, but it's only requiring 4 major values. There's S1, there's S2, there's N1, N2, and those are it. That's needed for running our formula. So definitely we don't want to go through a manual calculation on something like this. Even if we're with a calculator, we won't be able to do this by typing out every operation on the calculator. And so depending on some kind of technology that can quickly get the work done for us is going to be a good idea at this point. And so I highly encourage my students to use the program that I developed, or you can, some viewers with some programming experience can quickly write a little portable program similar to the one that I'm doing here. But then the idea now is that on my DF program that I have prepared for my students, then this S1 right here is asking for sample standard deviation 1. And so quite obviously we are going to enter 3 for our S1. Then I am going to enter, and notice how these values change. S2 was given to be 4.5, so I am going to enter 4.5. And the sample size that I picked from population 1, or sample size N1, is 400. And sample size N2 was also 400. And so now, after successfully entering all 4 required values into my DF program, then the degrees of freedom is calculated at the bottom box right here. So this is the degrees of freedom. And so back on my board, and you can see even before I'm getting back on my board right here, you can see that the degrees of freedom here is calculated as a decimal, which is something that's very likely to happen with a formula proven to be like this. And so for viewers, for public viewers out there, the truth is you can use, if you are on a powerful software that does stats, then your software program can be strong enough to even work with decimal degrees of freedom like the one we have here. Because I have experienced that in many the modern statistical software, then it is entirely okay and precise to have a degrees of freedom being in decimal like this. However, for students in my class, since some students are still not able to afford the use of an advanced software, so some of the more basic technology can only handle degrees of freedom being a whole value. So in that case, for my class, I always ask my students to round the decimal degrees of freedom to the nearest whole value. So it's just simply because I am aware that some of my students are not able to afford an advanced software program. So in that case, when we're in the desperate situation where any software program provided is only limited to a whole value degrees of freedom, then it's best to round the degrees of freedom, the decimal degrees of freedom, to the nearest whole value. And so in this case, with our particular problem here, then the degrees of freedom is decided to be 695. That's our degrees of freedom being used in this problem right here. And we can notice further that with this DF program that I wrote for my students, then once you enter the 4 required values, this program will also conveniently calculate the SEC for any of you. So what I'm saying now is that back in the step that I was calculating the SEC here, a lot of time later on, or maybe even in later example, you can see that I will just write down the setup but hold on to the actual final value, because I want to wait until we actually need to find degrees of freedom here, and one program of mine will provide the 2 values here in one work like that. And so we will also be able to find our T star value once we have had the SEC value. So now our degrees of freedom for the 2 samples together is concluded to be 695. And so just like a standard T procedure or a T test, we are going to now calculate the p-value for our 2 samples. The p-values that reflect how likely our D bar will stand on this bell curve. And so we're calculating p-value by firing up a probability calculation where I'm asking for among all D bar values out there. And now being a left tail, I am going to look for finding the probability that we find a D bar that is less than or equal negative 8.7. And that's how we find the p-value for our difference in the samples. And so this probability will be equivalent to, think about that, it will be graphically understood as the shading area to the left-hand side of negative 8.7 on this bell curve. But now since we don't have a z-score, but instead a T star score, then finding that area here must be done by doing the following work. I am going to run my LTCDF program. And so again, all that understanding that we have done all that past understanding about how to run a t-test, how to use a t-test is applied here. We're now going to run our LTCDF program. And again, my little LTCDF program now can become a little useful again. With my LTCDF program, I am going to enter minus 32.175, because that is the T star equivalent for this sample, equivalent to the sampling difference at this value, negative 8.7. And so, or if anybody else is using any other technology, instead of my LTCDF program, likely it will ask for T star value first. We are going to give it negative 32.175. And the next thing the program will ask for is the degrees of freedom. So I am going to provide 695 here. And so again, back on my calculators, my LTCDF program on the computer screen here, I am going to enter 695. And so this is how big that shaded area to the left of negative 8.7 on our current bell curve right here. This means on my writing board, our final p-value in the actual, in scientific notation, 4.36 times 10 to the negative 140. But that just simply, and as I keep saying, usually, unless being specified otherwise, throughout all of my video lectures in testing a hypothesis, I will round my p-value to 4 decimal places. So in 4 decimal places, this p-value of mine is 0.0000. And now that we have found our p-value here, then apparently this p-value of ours that we have calculated is much less than the significance level given in a problem. And so now again, allow me to quickly swing back at the information given here. We are looking at significance level 0.001 here. And so in that way, comparing our p-value with significance level, we are well below the significance level. And so now with all that reasoning that we have learned through our testing a hypothesis from past lecture, then this comparison here between p-value and significance level is now clearly indicating that our d bar as an interpretation, our d bar is an unlikely sample. And that's making d bar here. Our two samples together create a different d bar. That's making it strong evidence. And the strong evidence we have here is to either, we can say, to reject h sub 0. As we were saying earlier, h sub 0 here, if we were letting it, if we were accepting it to be true, then we led to a p-value way below our significance level. And so that's now making d bar here being a strong evidence to reject h sub 0. Or in another way of saying, we have strong evidence to support h1. And now, ultimately, since the question is looking for, as a yes or no question, are the samples showing strong evidence? We say yes if we have strong evidence, and we say no if we did not have strong evidence. And obviously, we had strong evidence here. So the ultimate answer to this question is yes, we have strong evidence. And now, in the same example, let's look at part B of our current example. And so all that information or all that descriptions regarding the two samples remain exactly the same. And so now part B of our current example, the question is asking us to construct a 99%. CI here stands for confidence intervals. So we want to construct a 99% confidence interval to estimate D. And so now, upon realizing that we are working in a problem that constructs a confidence interval, then we need to recall a couple concepts. And that is the reason why, again, back in the beginning of this lesson, I was saying that it is highly recommended that anyone arriving at this video lesson must master your skill in testing a hypothesis as well as finding a confidence interval. Because here I can only recall that some of the highlights about the concept. So we have drawn out throughout our studies in constructing a confidence interval that any final confidence interval is in the form of a sample value plus and minus a margin of error. And recall that this capital letter E is referred to as the margin of error. And so the sample value here is something that we can either always find that on our own purposely, or we can always have this as given information. And so in this case here, in our particular problem, we want to use the confidence interval to estimate D here. That's defined as the difference in population mean values. And so the corresponding sample value for that would make perfect sense to be the D bar value. So for our case here, in the work we're currently doing, the final confidence interval must be in the form of from where our given sample value, which is now in this case D bar, we must find out for ourselves how far up and down we can add and minus from this D bar, and that will be ultimately our final confidence interval. And so if we can now briefly look back at the entire structure of the problem as well as the given information. Now again, back from the beginning, what we mainly study here is the population mean age to reach high blood pressure, and then we separated this mean value into two separate populations. Population 1 is the man population. Population 2 is the woman population. And from each of these populations, we selected samples, and these are all given information. So further, from previous question, part A of our example, we have already found that with this current given sampling information, we have found for ourselves D bar right out from our two samples from the two populations here. Came out to be minus 8.7. And we have also found out the SEC value from our previous part of the example. So SEC, the combined standard error, is 0.2704, and the degrees of freedom is 695. So we will use these information shortly, but right now this is what I said earlier, that we have had for ourselves the sampling information. So consequently, we have already had this D bar value easily computed as minus 8.7. And so in that way, consequently, our final confidence interval, I am expecting that it must be taking negative 8.7 as the center. Then we are going to figure out a margin of error up and down from where our sample value was. And so in this case, the only thing we need to look for is a formula to calculate our margin of error for estimating the difference between two population mean values. So now margin of error in this problem, in this kind of problem, is given as T sub C multiplied with the SEC. And that is the formula we use to calculate the margin of error to estimate the difference in the two population means. And so now this is where this piece of information that we have calculated from part A will become very useful for us here. So we have already calculated SEC, or the combined standard error, to be 0.2704. So that means in this margin of error formula, we have already had that value being 0.2704. So what we mainly need now is the T sub C value. But a good news again, that if anyone is viewing this video lesson after you have already learned about how you can find a T interval, a confidence interval using a T value, then again we can quickly recall how we can find our T sub C. Note for yourself that our confidence level given in this problem, or required in this problem, is a 99%, or that is for later calculation, 0.99. So to calculate this T sub C, I am going to, as step 1, go with 0.5 plus 0.99 over 2, because the work here is it's always 0.5 plus half of the confidence level that we have, and provided the confidence level the confidence level is at is in a decimal expression like this. So the answer here comes out to be 0.995. And just like in lessons when we were still learning about how to find confidence interval using the T sub C, then we call this value here the left area, or area left. Then once we have had left area, we need to look for degrees of freedom of our samples. In this case, since we have two samples, so very similar arguments I've made in part A of the current example here, then this degrees of freedom can no longer be n minus 1. And so we now can legally use this degrees of freedom for the two samples we've had from our part A of the example. So now this work that we have found from part A now becomes useful. So degrees of freedom being 695 is what we are going to use for the next step in calculating our T sub C value. And so our degrees of freedom now is agreed to be 695. The last step in calculating T sub C is to run a program that's so-called INVT. Now, I have developed my own INVT program using Microsoft Excel, but INVT should also be given with any standard TI-83 or 84 calculator and many other commercial calculator, graphing calculators on the market out there. Will also offer similar program with likely the very same name right here that serve the exact same purpose. So when we're running the INVT command or the INVT program, the first thing the program will ask for is the left area. And if you're using any kind of technology on the market right here, then this is how a lot of times the syntax is going to run. We're going to call up the INVT command, and it will first ask for the left area. Then we're going to put in a comma, and we are going to enter our degrees of freedom, 695 in this case. And that's what we're using for our INVT program. And once we execute and run this program, the final value that comes out from this, from executing this command, from executing this technology right here, will be the value for T sub C. And so let's have a look to see how my own developed INVT program will work. So when you open the Microsoft Excel file that can be freely distributed for my students, or general public viewers out there can also get a hold of me in person to obtain a free copy of this program. But so this box right here, right underneath the label left area, is where we can enter the value 0.995, and because that's what the left area is to be indicated. And now you can notice that the T value here has already been changed. But now that's not the right degrees of freedom that we need to use. So here 695, and run that. And so now this is the final T sub C that I am going to be using. So it's 2.58292, and a lot longer. Now my Microsoft Excel in this case here only round to 5 decimals, but this value is supposedly a lot longer than that. And so now the T sub C I have found with the INVT program that I used, and it should be the same with any other technology that can have an INVT command. We find 2.58292, and a lot longer as our T sub C. And then, unless being specified otherwise, usually throughout my video lectures, I am going to round my T sub C to 3 decimal places. So 2.583 is my final T sub C value in this case. But again, I'm leaving that for my students and public viewers out there to watch for your own rounding requirements in each of the problems that you are doing anytime it comes to calculating T sub C value. All right, so again, with our margin of error to estimate the difference in two population means here to be T sub C multiplied with SEC. And after we have already found T sub C, and recall from our previous problem that SEC has been found to be 2.2704, then now we are ready to calculate our margin of error here. So the margin of error here in this case is 2.583. That's for T sub C, and we are multiplying with 0.2704. My final calculation came out to be 0.698 for 432, and a lot longer. And in this particular problem, I am going to round to 2 decimals. But I leave that again for viewers and my students to watch for rounding requirements in each different problems. That's finding a confidence interval or finding a margin of error. So here, because this is h, so I feel it's best to round h to 2 decimal places, the expression. So and in this case, we're forced to round to only 1 decimal place. So 0.7 is our final margin of error. So what it says now is that at 99% confidence level, we know now that our confidence interval is in the form of centering at negative 8.7. It is going to be up and down by 0.7. And that's our final confidence interval. And so I said it is going to be up and down by 0.7 from our sampling difference in the 2 sample means here. So what is it? The difference in mu1 minus mu2. The difference mu1 minus mu2 is at 99% successful level, guaranteed to be anywhere 0.7 years up and down from negative 8.7. And then we can also bring this interval into traditional format by simply subtracting this margin of error from the center of value and also adding this value to the centering value. And so subtracting this margin of error from the centering value, we're looking at negative 9.4. And that's the low end of our interval. And so the high end of our interval here is going to be 0.7 plus minus 8.7. So that gives us minus 8. And so we have a confidence interval in traditional format right here. And admittedly, a lot of times that students in statistics are required to be able to express a final interval, confidence interval in this form right here, where we have the sampling value in the middle and up and down by the margin of error. But be ready to be able to display your interval in 2 different formats right here. And so again, at 99% successful level, this difference between mu1 and mu2 is guaranteed to be somewhere inside of this interval, anywhere between the low end negative 9.4 and the high end negative 8. And so before we completely move out and be finished with example 1, with this current example, part B right here, then let me make some good connection between the result we have done in part A and the result we have done in part B just now. So in part A, we have successfully proven, so now I have to mention again that we have proven, what we have proven there is that we had strong evidence that our difference is a negative difference because we had strong evidence to support H1. And that's what the result said back in part A. But all we can say at the end of part A is that we can support H1 saying that the difference mu1 minus mu2 is a negative difference. But at the end of part A, we did not know how far negative this difference can be. And so now the result in part B will come in and connect as a useful and further clarification of the result from part A. Look at how we have already guaranteed. The difference now, well, after part A, it was supported to be below 0. But now we further knew that at this interval, this difference d right here is inside of our interval anywhere between the low end negative 9.4 and the negative 8, and successful at 99% level. And so look at how negative this interval is. And so this is how I can see the consistency between the result we have found in part B and the result that we have done back in part A. And so this interval, in addition, gives us a better picture of where our d, our difference in mu1 and mu2 should belong after we have found the result from the part A. The same example, and now let's look at a different question as part C of our current example here. So anyone can notice here that the entire description of all samples remains exactly the same here. And so now question C is asking, at significance level 0.001, are the samples showing strong evidence that the mean H to have HBP, so again HBP is short for high blood pressure, in the two populations is different from each other. And so obviously, based on the wording of this kind of question, are the samples showing strong evidence? So we're interested in knowing whether we're having strong evidence or not. So this immediately tells us, the phrase that I just now highlight immediately tells us that this question brings us back to a testing a hypothesis problem. So let's get to it. And so to test a hypothesis, again, let's first identify what the two hypotheses are. So as the question here is saying, are the samples showing strong evidence that the mean H is indeed, now we're studying into population, so mean H is mu1 and mu2. But so are we having strong evidence that the mean H to have HBP in the two populations is in the two populations? That's why I was indicating mu1 and mu2, but it's different from each other. So now with this phrase right here, back on my writing board as I was sketching down a note earlier, so we want to prove that based on the data, the evidence provided from the two samples, we want to prove the fact that mu1 is other than mu2. And so I'm going to now stick on my writing board for another while. Mu1 is other than mu2 or different from mu2 is the same algebraically as mu1 minus mu2 is other than 0. Or we can also write that as mu2 minus mu1 other than 0. These are all different algebraic re-expressions of our inequality right here. And again, as I mentioned in the general lecture, that when we're comparing two population mean values, or generally later on we will learn that anytime we're comparing two population values or parameters, then we always want to compare in terms of seeing the comparison. We always want to see the comparisons in terms of the difference between the two values here. But then, as I also mentioned as a convention, that we will purposely choose this particular expression right here, even though both of these are all correct algebraically, but we chose this particular one that I just now circled simply because we always want the value that came out from population 1 minus the value that came out from population 2 as a difference. And so now mu1 minus mu2, recall from our definition that we have seen in the general lecture, that is our unique d value. So d here is the difference mu1 minus mu2. So here we can see that the statement right out from the wording of the question is stating that d, the difference, is other than 0. And so the same reasoning as how I have been explaining in the concept of testing a hypothesis, since the statement here directly involves an inequality, the statement must be an alternative hypothesis, or symbolically H1. And so now, once we've had H1, H0 can be easily found by simply rewriting the statement in H1, but replace the inequality with the equal sign. And there we have for ourselves the null hypothesis. So now these are the two hypotheses that we are testing for our testing hypothesis problem currently. And now with our experience in testing a hypothesis, we know that anytime seeing an alternative hypothesis with this inequality, we must run a two-tailed test. And so for our current question here, we can utilize a lot of information that was found from earlier question. So these are the given information. These are the samples that are still being listed here. And from the two samples that we are currently having in hand, then we can find for ourselves the sampling difference, or the difference in the two sample mean values. So the difference in the two sample mean values here is a negative 8.7. For I was doing, as a recall, x bar 1 minus x bar 2, and that's what this is. And the two samples that we have here gave us a combined standard error, or in symbolic form SEC right here, that we calculated in earlier part of the example to be 0.2704. So this information can now also be useful for us, and we have also calculated in earlier questions that the degrees of freedom of the two same samples here is going to be 695. And so now for our current problem right here, for our current question, now I'm going to start out by starting with the reasoning as following. If we are currently accepting h sub 0 to be true, or what if h sub 0 was true? And h sub 0 is saying the difference in the two population means equals 0. So if that h sub 0 was true, then the extended central limits theorem, according to what we have learned briefly, guarantees us that the center of all d bar, of all sampling differences, because I've shown earlier that we already had a d bar, but our d bar is only one among infinitely many other d bars. And so the center, or the population mean of all d bar values must equal to d, and consequently in this case d equals 0. So in our case, this must be mu, consequently mu d bar must consequently equal 0, because we're accepting d equals 0. We won't be able to find for ourselves sigma d bar, and the argument is very similar to part A that we have seen. But now instead we can use a close enough approximate of sigma d bar. That is the SEC right here. And so the SEC here was calculated from earlier question to be 0.2704. And again, recall that even though being a random variable, a continuous random variable, but here I'm using a lowercase letter. But now seeing d bar as a random variable, then it means it represents any difference. So it represents a difference between an x bar 1 and an x bar 2. And so upon realizing that d bar is a difference, represents any difference between an x bar 1 value and an x bar 2 value, then the extended central limit theorem can also lead us to knowing that d bar will be, or at least approximately, on a normal distribution with center at 0, because the center is the mu d bar. And with average spread on this bell curve, the unknown sigma d bar value. So we know we have a bell curve for our random variable here. And so that is a consequence. So once we know that consequence from the extended central limit theorem, we can now draw for ourselves a bell curve that represents all values of the sampling difference between an x bar 1 and an x bar 2. This bell curve will have center at 0. And our particular d bar that we've had is negative 8.7, which stands somewhere to the left-hand side of the bell curve center. And so the next step now, after realizing that our d bar is on a bell curve, then we are going to now calculate the t star value for our bell curve. So drawing some experience out of question part A, then t star generally is anytime we're comparing two population mean values, and we can just take right from where our sampling difference is, we're subtracting 0, which is theoretically the mu of d bar value, and we are going to divide that by the SEC that we have calculated previously. So this is a formula for t star, something that we can draw out from part A of our work earlier. And so in that way, that means t star that we're about to have now is going to be a minus 8.7 and minus 0, of course. And again, this 0 is because we are actually subtracting the mean, the center of this bell curve right here. And we divide it by the SEC, which is an approximate to the sigma d bar value. So here in our case, we already had that value for SEC being 0.2704. So now that our t star value came out after my calculation to be minus 32.175. So at this point, if anyone is rolling back to the solution for part A, then the steps are exactly the same, including the steps where we are taking the degrees of freedom, which I will mention later. And the next step from here is usually to calculate the degrees of freedom for our two samples. But since this problem here takes all of the information we have done back in part A, and so I have already shown on the board earlier that the degrees of freedom for the two exact same samples we already had was calculated, even though the formula was a very messy formula, to be 695. So just as a quick reminder, we used the following formula: S1 square over N1 plus S2 square over N2 square, and divide that by 1 over N1 minus 1 times S1 square over N1 all square plus 1 over N2 minus 1 times S2 square over N2 and squared again. So this was the formula I introduced in part A to calculate the degrees of freedom. It will take a more advanced course to understand why a formula like this is chosen. But This happens to be the degrees of freedom formula that gives the most precise degrees of freedom in our case here, doing 2 independent samples. And so I also explained earlier that anyone calculating the degrees of freedom with this formula can use a software of some kind or the DF program that I wrote that runs with Microsoft Excel. My students or viewers who have access to this program of mine can just simply click on the tab at the bottom that says DF here, and this is where we enter all the value S1, S2, N1, N2, and the degrees of freedom will come out and calculate it. This program will also calculate the SEC for any one of us. So from part A of the example, and it makes sense that a formula like this will always give a decimal. So I was saying earlier that for public viewers who are viewing this video, then you can just go with whichever the decimal degrees of freedom that came out from the calculation. But for students in my class, I decided to go with to round the degrees of freedom that came out from this formula to the nearest whole value. So that's another reminder. We round to the nearest whole value. And then I will never ask any of my students, and the same with the public viewers out there, your own professors should never ask for this degrees of freedom to be done by hand, by manual calculation. So you should have some kind of technology that can help you, that can assist you to quickly find the value for this. And now once we have had our degrees of freedom for the 2 samples to be 695, now at this step we're taking the p-value, calculating the p-value. We are going to work in a different direction compared to part A over here. We will still calculate a probability. The probability where on this bell curve we are interested in finding a sampling difference, or the difference in the 2 samples, being again our sample had a negative sign. So I am going to use it is the very same logic that anyone here must have seen back in the day we were doing, back in the lectures where we were doing formally learning about testing a hypothesis. So here, having a negative t-score, we are going to fire up a less than or equal inequality, and this is minus 8.7. The work for part A to calculate p-value is simply this calculation, but now for our part C here, since we're doing a two-tail test, we must multiply this probability by 2. So this is 2 times, and it's odd. And so again, this inequality pointing to the left is due to the fact that we have a negative z-score, and that's why it's resulted here, where I did not emphasize this back in part A. But then now, being a two-tail test, what's critical to decide here is that since the t-score is a negative t-score, we have to use the left tail inequality, but then we multiply that with a factor of 2. And so now to actually fire up the calculation here, it's just a matter of running some kind of technology that can help us into this work. I developed for myself a program that's called LTCDF program. But the idea now is to find, this program is to find how much area on this bell curve shaded to the left hand side of our sample negative 8.7, supposedly somewhere already on the left hand side of the bell curve center here. So that's what the LTCDF program is for. Outside of my own LTCDF program that I have developed for my students, then I believe there are many other software programs out there that will do the same purpose here. So very general, and just like any other program that does a similar functionality, an LTCDF program, first thing we'll ask for the t-score. So here we are going to give a negative 32.175, and the next thing after the t-score, degrees of freedom will be asked for. 695. And then we'll go multiply that result by 2. So now let's have a look at my Microsoft Excel program, my LTCDF program that's written with Microsoft Excel. So this box right here underneath the label T is where we can enter our T value. So mine is 32.175. Hit enter, and notice it already started changing some of the left area value that it indicated here. But let's go further. So I'm going to go to this box and change my degrees of freedom to 695. And so now with this degrees of freedom, 695, we came up with the answer. So this answer 4.36e negative 140. This answer is supposedly how big that area shaded to the left hand side of negative 8.7 on our curtain bell curve here. And the answer that anyone have seen on the Microsoft Excel screen means we're looking at an answer that is 4.36 times 10 to the negative 140. But then we need to multiply this value by 2. And so the final p-value, I will always use 4 decimal places unless being specified otherwise. So 0.0000, even after we have already doubled. So now that our final p-value is concluded to be 0.0000. And so now that we have come to our final p-value being 0.0000, then the next step is to compare this p-value. Because this what we're doing here is a testing hypothesis problem. So we need to compare our p-value with the significance level. So we need to compare this. Is it going to be less than or greater than? That's what we need to find out. And so back to the question itself right here, we are given a significance level of 0.001 as it sets here at alpha equals 0.001. So that means our final p-value must be compared with 0.001. And the direct comparison like this immediately shows that our p-value is well below the significance level given in a problem. And so that's now indicating that as of this point, for anyone viewing this video and combined with your experience in testing a hypothesis, then anytime your p-value of the test falls below the significance level, that's where we can say that your particular sample, in this case is the sampling difference in the two sample means right here, is an unlikely sample. That's the first thing we can see, we can understand about this result. Being an unlikely sample makes our D bar here strong evidence. And now I can say D bar is strong evidence. And now, having a strong evidence here, the first thing we can do, we can use that strong evidence to reject H sub 0. Or we can also say that we have D bar as strong evidence to support H1. So there are two different ways how we can interpret our final result here as having strong evidence. And so reject H sub 0 because H sub 0 was at first accepted to be true, and now we have strong evidence to reject that. But then it also means logically the same as supporting H1 with this strong evidence. And then one more time, looking back at the question itself, the question in the end remains as a yes or no question, simply in the way it is. Are the samples showing strong evidence? So, as a yes or no question, now it is clearly that our samples are showing strong evidence. The samples together created this D value, and this D now is a strong evidence. For us to either reject H of 0 or to support H1, then now the answer ultimately is yes. All right, so we are now at question D of our current example. And so it is, of course, that the description of our two samples remains exactly the same here. And so let's spend some time reading the wording of the question in part D right here. So at significance level alpha equals 0.001 are the samples showing strong evidence that mean age to have HBP, that stands for high blood pressure, in female is greater than that in male. And so before we really proceed any further into analyzing and breaking down the question itself right here, let me, I just want to ensure anybody viewing this video to notice the following. Now, if I quickly bring back question A right here for anyone viewing the video to compare, then here it is. This was our question A that we already had a solution for. And so now in question D, at this point anyone viewing the video will notice that question D is exactly the same as question A. So what is the purpose that I brought up another problem for us to do here, which is the exact same problem that we already had a solution for? So allow me to introduce my intention for bringing up the exact same problem, where I call it, I treat it like a brand new problem, but it was essentially the exact same problem that we have done in part A right here. So provided that we know all that sampling information remains the same, and the question itself also remains exactly the same. But so now, unlike part A that we have learned, think about if we were back at the beginning when we were first trying to get our hands, setting our hands on this and making a plan here. Then now on my writing board here, think about the two populations. And my point now is that back to the two labeling conventions right from the beginning. I could have made my choice to give the numerical label 1 for the woman population. Or in other words, so woman population now is referred as population 1. And that means consequently the mean age to have high blood pressure in population 1 now is referred as mu1, as we already have learned that general convention. And so the sample size, as a further consequence here, is that the sample size that we decide for all samples from population 1 can be referred to as sample size n1. And then the sample mean that we have obtained from population 1 here, we can now call that x bar 1. So I purposely brought up, and this is my intention right here, I purposely brought up this question D, which is exactly the same as question A, but we roll back to that beginning point where we decided the labeling convention in a way that is completely opposite from part A. And so standard deviation of the sample we had from population 1 is called S1. So in that same way, now if I chose a numerical label number 1 for woman population, then the man population, of course, gets that label 2. And this is population, of course, population 2. And so the sample size that we use for all samples from population 2 is now referred as sample size n2. So further, as a consequence, the sample mean of the sample from population 2 here is referred to as sample mean x bar 2, and so on. This is S2. And that is my intention for bringing up the exact same question, but we treating that as a completely brand new problem, all because we started out by giving the numerical labeling completely opposite from the earlier solution. And of course, this is mu2. But now, again, just like how I explained in a general discussion, then doesn't matter how we decide to give the labeling, the numerical labeling conventions here. The definition for these, for the difference in mu1 and mu2 remains exactly the same. We always want mu1 minus mu2 to be d, to equal d. And we always want to define d bar as the difference in a sample mean from population 1 minus a sample mean from population 2. And this is the meaning of the two values x bar 1 and x bar 2. And of course, again, since we're working with unmatched and independent samples, so n1 and n2 do not have to equal, even though in our case right here, it happens to be n1 and n2 are equal value. And so in this way, immediately as a first impact, as a first consequence, then unlike part A or opposite from part A, our d bar now will be calculated as, now recall that we always going to need x bar 1 minus x bar 2. So here we're looking at 51.2 minus 42.5. And the answer now comes out consequently as a positive 8.7. And let me now purposely write the sign, even though I know normally we don't have to when anytime it's a positive value, but I purposely write the sign and indicate that with the red ink right here so that anyone can notice the problem, the structure of the problems remain almost identically the same with how we solved part A, how we came up with the solution in part A, except for things are going in the opposite way right here. So back in part A, this was negative 8.7, and now this is positive 8.7. And so eventually we will get to SEC as well as degrees of freedom, because these two values are all required parts that we need to perform the test. And so as a reminder again, the degrees of freedom, as we have learned in earlier questions, runs through a very messy formula. And SEC here, the combined standard error, is found by the square root of S1 square over N1 plus S2 square over N2. So even though we switch the labeling convention, but it looks like the formula for SEC remains exactly the same, where it requires the four important values N1, N2, S1, and S2. And then just like the earlier question, I am going to let my DF program to at once give the DF, the degrees of freedom, and the SEC, and the combined standard error. So now with my DF program, right here, I am going to provide, so this time we're going to switch the rows of S1 and S2. So S1 in our work is going to be, in our current work now, is going to be 4.5. So opposite from part A. And S2 now is going to be 3. The two sample sizes remain the same, 400 and 400 for N2. And so now, as I keep saying, the program that I developed for my students that runs in Microsoft Excel right here will give two answers. One is for the degrees of freedom and one is for SEC. And you can algebraically, anyone viewing the video with some good algebra background can verify the reason why it should arrive at the exact same answers with what we have had in part A, and also the same with what we used in part C earlier. And so now SEC is concluded to be, and as I have always mentioned, unless being specified otherwise, I will always round the SEC in 4 decimal places. So 0.2704 is my final combined standard error. And the degrees of freedom here, as I have mentioned in earlier questions, in earlier work, and we will always, for my class in particular, I will highly recommend my students to round to the nearest whole value. 6 95, which is the nearest whole value of the result we found here. And so now back to the question itself, and let's read into the wording a little more right here. So at significance level alpha equals 0.001 are the samples showing strong evidence that mean age to have high blood pressure in female is greater than that in male. So we want to prove that mean age to have HBP in female. So thus immediately on scratch work here. So let me now switch to my writing board. But now that we have already switched our numerical labels on the two populations in the opposite way. So mean age to have HBP in female is now referred to as regarded as mu1. So directly from this wording right here, we want to prove that mean age to have HBP in female is greater than that in male. So that means now we're trying to prove, we're looking at a statement saying that we're trying to prove that mu1 is greater than mu2. So this is directly right out from the wording of the question itself. And at this point, anyone viewing the video here must now be fully aware that we will always look at a comparison in terms of a difference. So mu1 greater than mu2 is the same as saying mu1 minus mu2 greater than 0 algebraically. Or we can also say mu2 minus mu1 is less than 0. These are the two algebraic equivalent forms of this comparison statement as an inequality. But since we define our D, as anyone have already knew, to be mu1 always population value from population 1 minus the value from population 2. So D equals mu1 minus mu2. So for that reason, we will go with this form right here. One more time, looking back at the question itself, are the samples showing strong evidence that mean age to have HBP in female is greater than that in male. And so in that way now, on my writing board, I can see that the statement is saying that we want to prove that the difference mu1 minus mu2 is a positive quantity. And so here we have for ourselves the alternative hypothesis H1 that we have successfully nailed down. And again, in our experience at this point, testing a hypothesis, then anytime we have already had H1 successfully nailed down, we can easily come up with H sub 0, the null hypothesis, by simply rewriting the statement in H1, but replace the inequality here with the equal sign. And so now this is the part where it makes it opposite from the work we have done in part A, even though we will achieve the exact same result because we are working with the exact same question. Here, just I'm trying to point out a solution that is completely opposite direction, but it will come out with the exact same result. And so in part A, the hypothesis, the alternative hypothesis was bringing up for us a left tail test. But here now in question D, after we switch the numerical labeling, this problem now, the hypothesis here is indicating for us that we're working with a right tail test. And that's the first thing making it completely opposite from the work we have done in part A. And so now I am going to start out as usual by accepting H sub 0. So if we were accepting H sub 0 to be the truth, so if H sub 0 was true, stating that the difference between the two population means mu1 and mu2 equal to 0, then according to the extended central limits theorem, we know that the center of all d bar values, because once again I have to remind anyone viewing the video here, d bar that we have here is only one sample value that we have among infinitely many other sample values out there. And so this mu d bar is the average or the population mean of all existing d bar values out there, which is also the same as the center of all d bar values. And this mu d bar theoretically equals d, which will consequently equal 0 in our case right here. Average spread sigma d bar, or the standard deviation, the population standard deviation of all sigma of all d bar values, does exist. However, unfortunately, we won't be able to find that because we don't know sigma 1 and sigma 2. So instead, we will be using a close enough approximate to substitute for sigma d bar. And as I said just now, SEC, the combined standard error, is usually close enough. So we are now accepting 0.2704 as a close enough substitute for sigma d bar over here. And we have already calculated this value just earlier in this particular work. And then again, at this point, we are fully aware that d bar itself, even though a lowercase letter, but it is a random variable, and as a matter of fact, a continuous random variable. And it represents a difference, or any difference, in an x bar 1 and an x bar 2. So it's just a difference in any pairs of x bar 1 and x bar 2 that we can pair up, that we can pick. And so we have also learned throughout my general discussion that d bar can generally be assumed to be on a bell curve centering at 0, which is theoretically this value d, or mu d bar right here. But since we are currently accepting that 0 is the value, and so this is further can be regarded as a consequence as well. So d bar can be assumed to be on a bell curve with taking center consequently at 0 and the unknown average spread sigma d bar. And so in that way, further, we can now draw a bell curve to represent all values of d bar where the center of this bell curve is right at 0. But now, completely opposite from part A, our particular sample value d bar that we are particularly having is now a positive 8.7, no longer negative 8.7 like what we've had in part A. And so this, in the way how it is right now, this d bar must stand somewhere to the right hand side on this bell curve right here. And then in the same way, for our current sample that we have, we can calculate a t star value. And t star value will permanently use that formula from where our current sample value is. We will subtract 0, which is theoretically the center of this current bell curve that we're on. And we divide by the SEC. And so this is the highlighted formula that was introduced throughout many questions. But now in the actual calculation, we're looking at now positive 8.7 divided by 0.2704. And so I don't need to worry much about the calculation because pretty much everything is just the opposite of the result we found in part A. And so in part A, it was a negative 32.175. It was negative in part A. And so here it is now going to be positive 32.175 as our t-score. And yes, I should have also mentioned that I should have also put that positive sign in red ink as well. And so now we're going to briefly, as the usual step, after getting t-score, we are going to find the degrees of freedom of our two samples. However, here since we already had the degrees of freedom from previous questions, we can go ahead and reuse that. So I'm gonna, for this step, I am just simply restating that the degrees of freedom we have been using is 695 right here. And so after these steps, we are now going to calculate the p-value of our current sample. And so now, opposite from the work in part A, here our work is a right tail test. The test we're proceeding is a right tail test. That means anywhere our sample stands on this bell curve, we must be calculating p-value as the area shaded to the right hand side of where my sample stands. And so in that way, here is the setup of the calculation work. We want to find the probability that among all sample d bar values out there, we want to find a chance that our d bar is greater than or equal 8.7. And so it's a right tail test, and that's the reason why I'm using this right tail inequality. And so now to find this area, again, now we must use a technology of some kind. I have developed for my students a program that's called LTCDF that will ask for the t-score of our sample. So t-score in our sample here is 32.175. And further, my LTCDF program will also ask for degrees of freedom, which is what we have restated here from previous problems, 695. And so again, I have to mention that once we run this program, it only gives the approximates to the area shaded to the left-hand side of the sample on this bell curve. But since we are doing we are calculating or at least an approximate, a close enough approximates to the area that's shaded to the right-hand side of 8.7 of our sample on this bell curve. So we need to subtract the answer from the LTCDF program from 1. And that is how we are setting up the structure. And again, I can also mention that so without having a copy of this LTCDF program that I developed for here, there are many other web programs or many other programs being sold on the market out there that can do the similar purpose, that finding an area shaded to the left of a t-score at a given degrees of freedom. And likely once you have your own technology, the command will run similarly by asking the t-score first with a comma and then the degrees of freedom. So now on my program here with Microsoft Excel, I can quickly click on the LTCDF program as a tab at the bottom here. And now in the box right underneath the label that says t-score, this is where we enter this time positive 32.175. And then I am going to, and then that will quickly change my value. And here the degrees of freedom is 695. And so anyone viewing the video, you can notice the area here shaded to the left is 1. But that is the area shaded to the left. So for our actual p-value, that is the area shaded to the right-hand side. Then we are doing 1 minus 1. And that gives us the final value, p-value 0.0000. And so now that we have arrived at our final p-value, still remains 0.0000, even though the work that we did was completely the opposite direction. But now when it comes to this point, the result will agree exactly with the result we have found in part A. So just as usual, now that we have come to successfully calculating final p-value, then the next step is to compare the p-value that we have obtained with the significance level. We want to find out whether it's less than or greater than the significance level. And so with the wording given in the question here, then we are given the significance level to be 0.001. So now that our final p-value will be compared with 0.001, and direct comparison shows that our final p-value is well below the significance level. And so now, as usual, in the experience we have already had so many times throughout working on testing a hypothesis, then anytime we have achieved a final calculated p-value being less than the significance level given here, then we now can conclude that our sample, in this case as a d bar, is an unlikely sample. And being an unlikely sample leads to d bar itself is showing strong evidence. And this strong evidence here is for us to say that either we can reject h sub 0, or we can also say the strong evidence is for us to support h sub 1. So I'm saying we reject h sub 0 is because h sub 0 in the beginning was accepted to be the truth, and now with d bar being strong evidence, we are now rejecting h sub 0, because accepting h sub 0 as the truth here led to all these conflicts right here, and consequently the p-value is falling below 0.001 and making our sample a very unlikely sample, and that's why our sample is strong evidence to reject h sub 0. But then ultimately for the question itself, it's a yes or no question, because it's asking, are the samples showing strong evidence? So what we mainly looking for was whether we had strong evidence or not, and we apparently did find out that our sample is showing strong evidence. So in that way, the answer to this question, this ultimate question we have now, is yes, our sample or our samples are showing strong evidence. Now, so d bar is one sample value, but it came from two samples that we created this difference, and so that's why it's d bar is a strong evidence. But that means it means equivalent with the question itself, that the two samples before calculating d bar are showing strong evidence. And now we are again saying yes.